surface chemistry. Surface chemistry means something to do with the surface of anything. Generally, who will provide a good surface? Solid surfaces. Of course, there will be liquid surface. Gas, it has no meaning. Basically, why we are interested in the surface? We have got so many wonderful phenomena taking place and so much of application only because of the surface of any medium. Why surface is so important? And first of all, what is surface? Suppose you select some solid itself, some solid. As we have seen in solid state chemistry, a bulk will have so many particles. If you have a bulk particle, it is attracted from all sides. If you take any bulk particle that is having so much of force balance because of the molecules or particles surrounding it. Whereas, if you take a surface if you take, that cannot enjoy that many attractions from the other particles, because the surface particle is limited to the surrounding particles only on the one side. The other side of the surface, there are no particles. And how much can you take as surface? Almost, if you take a solid, a depth of 100 nanometers, something like that, you can take as solid surface, and beneath that you can take it as bulk. In a bulk, you will have the particle surrounded by many molecules and it will enjoy much more attraction compared to a particle on the surface. So, if you take a surface particle, the surface particle cannot enjoy that much attraction. It is limited to one partial set of particles inside the bulk. So, in these two particles, who has more energy, who has less energy? If you take a bulk particle, it is attracted by many. One which is enjoying more attraction, will be of lesser energy. Attraction leads to loss of energy. The one with relatively lesser attraction will have greater energy. So, from this small basic physics, we can clearly understand why the surface is more active than the bulk. In the bulk, molecules are saturated with attractions. On the surface, molecules are partially saturated with attractions. So, in the surface, the molecules are more energetic. So, they try to satisfy their unfinished valencies. Unfinished valencies means what? All the valencies of the particles on the surface are not satisfied, not saturated. So, they will show a tendency to get the unfinished valencies to be satisfied or unfinished attraction to be saturated. So, in that process, the surface molecules will show a tendency to catch up the particles from the nearby vicinity. Suppose there are some particles over here of some other substance, they will try to catch them. So, in the process, there will be an attraction of the particles of the second substance. There will be an attraction of the particles of a second substance. The attraction leads to accumulation on the surface. So, if you have any surface, the particles get attracted and get accumulated here. And this may happen even into the bulk in some cases. Suppose you keep a sponge in water, the sponge will pick up water into the bulk because they can enjoy more attractions inside. There are still some more unfinished attractions inside. So, the particles will go into the bulk. So, it is all the game of minimizing the energy of a system. Sometimes the particles may stay and they may go inside the bulk also, both may happen. Particles of the second substance may enter into the bulk of the first substance. Definitely here you are involving two substances. One substance is in the bulk form, in solid form. The other substance, assume it is a liquid or gas coming from outside. The particles will be attracted by the surface, and sometimes the particles may go into the bulk if at all there is some other valencies left. generally that is called absorption. If you have any substance which is taking particles into the bulk from outside, we call such phenomenon as absorption. If the particles of the second substance stay only on the surface, get accumulated on the surface, it is confined to the surface, restricted to surface, limited to the surface, we call such phenomenon as adsorption. You have got absorption, adsorption, sorption, desorption. Suppose the particles are escaping out from the surface, suppose there is surface, they are escaping out due to heating or any other phenomenon, whatever may be the case. If the particles are going out of the surface, we call them such phenomenon as desorption. So, we have many varieties of such things. Because the chapter heading is surface chemistry, we will be discussing extensively only on adsorption. Let us just visualize some processes. Suppose this is a substance, that pink color is a substance. So, this is providing surface, that belt like thing is a surface. See, this is providing its surface, and as I said, this is bulk and this is surface. The bulk particles are, they are less energetic because they are more attracted compared to the surface particles. Surface particles are less attracted, they have more energy. So, they will be showing a tendency to minimize their energy by attracting the particles of nearby substances. Just like on your television, some dust particles may settle down. If you do not touch any book for some time, you can see some dust settling on the book. So, this is all adsorption kind of a thing. So, surface. So, let us see how the particles may, sometimes they enter into the bulk, sometimes they are confined to surface, sometimes they may do both, like that. See how they are coming. What are they doing? They are going into the, most of the particles are entering into the surface, into the bulk. See, most of the molecules are going into bulk, we call it absorption. Suppose you keep a chalk piece in ink, the chalk piece will absorb the ink. We call such phenomenon as absorption. Most of the molecules are going into the bulk, it is a bulk phenomenon. So, if you think again the other manner, there is surface, there are particles, see what happens. Where are they accumulated? Yes, they are confined to the surface. See, on the surface they are staying. The particles are just spread on the surface. This is called physical adsorption. This is called physical adsorption. The second one you see, there is a small difference. This is called chemical adsorption. In previous case and present case, what have you observed? See, just once again you observe, the particles are going into the bulk, little left on the surface, generally most of them will go into the bulk only, that is absorption. Now you see, this case particles are staying on the surface just like that, they are only staying on the surface, they are not going into bulk. What else you have observed in this particular case? There is one layer of particles and there is one layer of particles settling. Once again you observe, one layer of particles are settling and one more layer of particles settling on the already settled particles, and one more layer is also settled. This is called physical adsorption, this is called physisorption. And in the next case you observe, the particles are penetrating partially into the surface, this is called chemical adsorption, there are bonds happening. So, like this we have got some good language in surface chemistry, and some particles may escape from the surface also, see they are escaping. See, this is called desorption, that is called desorption, particles escaping from the surface. So, we have got what should I tell, the particles settling on the surface, entering into the bulk. See, sometimes even bulk will take, even the surface will take, this is called sorption. See, particles entering into the bulk, particles staying on the surface is called sorption, particles entering into the bulk completely is called absorption, particles confined to the surface itself is called adsorption, particles escaping from surface is called desorption. We have got so many phenomena like this, and let us now confine, because our chapter heading is surface chemistry, let us confine to a phenomenon where only surface is involved. So, for that sake I think we need to learn some definitions, that we will do now. Some definitions are required to understand this particular surface chemistry adsorption phenomenon. So, as we have seen, the particles are confined to the surface like this. What is this called? Adsorption. And you have seen the substance which provides the surface, and this is the substance which is entering into the surface, entering onto the surface, and this substance is called adsorbent. Adsorbent. What do you mean by adsorbent? A substance which provides its surface for adsorption to take place, and these are what the particles of the second substance which are attracted and subsequently accumulated, and these are called adsorbate. This is adsorbent, that is adsorbate. Adsorbent and adsorbate. So, this is a very interesting phenomenon. A substance provides a surface, another substance provides the particles to settle on it. So, the process is called adsorption. The attraction and subsequent accumulation of the particles of one substance on the surface of other substance is called adsorption. You must learn this language. The substance which provides the surface is called adsorbent. The substance whose particles settle down on the adsorbent surface is called adsorbate. Suppose you have painted a wall, you can call the wall as adsorbent, you can call the paint as adsorbate. Because wall is providing its surface, paint is occupying the surface. So, you can call it adsorbent and adsorbate. Wall is adsorbent, paint is adsorbate. So, this is adsorption phenomenon, this is adsorbent, this is adsorbate. Suppose you have lot of charcoal, coconut charcoal, this is all coconut charcoal on which suppose some xenon is settling on the surface. Here we call the charcoal as adsorbent and xenon gas as adsorbate, adsorbent and adsorbate. This language you better learn. And the spelling is adsorbent, D means what? We are confining only to the surface level. We are not discussing about sorption, we are not discussing about absorption, we are not at present discussing about desorption. Right now we are speaking about adsorption, surface accumulation of one substance on the other substance. In this adsorption, we have seen a surface like this. So, this is adsorbent. What is happening? The molecules or particles of the other substance are settling on the surface. There must be attraction, otherwise the molecules cannot settle on the surface. So, let us now see how the molecules are settling. Suppose the molecules are just falling on this and settling like this. You may ask me, what is their interest? So, there should be an attraction. Attraction leads to loss of energy. So, some energy is lost. So, delta H is negative. Wherever there is some energy lost at a given time pressure, that is delta H negative. enthalpy change is negative. Suppose the molecules are originally free before this adsorption phenomenon. See, the molecules are here and there like this. You have seen they are free molecules with high entropy, but once they come and fall on this, they lose their freedom. Once their freedom is lost, so what will it be doing? It loses its entropy. So, this is also an entropy loss phenomenon, and because it is happening, delta G is also negative. So, during adsorption some heat is lost, so exothermic process. The molecules lose their freedom and settle down on the surface. So, if the randomness is lost, we call it loss of entropy. So, delta S is negative, and anything happening spontaneously, we call it delta G negative, Gibbs energy loss. So, this is how we have to keep some words in mind, some phenomenon in mind before actually entering into the subject. So far you have learnt the word adsorbent, adsorbate, gaseous adsorbate, getting settled on adsorbent. During adsorption, delta H negative, delta S negative, delta G negative, that also you keep in mind. Now coming to the classes of this adsorption, we have two varieties of adsorption basing on the type of attraction between adsorbent and adsorbate. See, basically the surface may attract this through van der Waals force. This is just van der Waals force between adsorbent particles and adsorbent surface and adsorbate particle. If it is just van der Waals force of attraction, such adsorption is called physisorption, physical adsorption. The attraction is just van der Waals force between adsorbent and adsorbate particles, is just van der Waals force, no well defined bond, just small attraction. Such adsorption is called physical adsorption or physisorption. Suppose the surface is, this is the surface, the adsorbent particles, adsorbate particles are connected to the adsorbent like this. See, there is a strong bond, this is all surface. There is a bond between molecules and adsorbate molecules and adsorbent surface. If such bond exists, we call it chemisorption. Physical adsorption, chemical adsorption. Physical adsorption is just accumulation with van der Waals force. Just van der Waals force. Chemical adsorption is a chemical bond. There is a chemical bond between adsorbate and adsorbent. So, these molecules settle on the surface through bonding, chemical bonding, whatever type of bond it may be. But this adsorption is not through chemical bonding. Adsorbate substance, adsorbate molecules settle on the adsorbent through mere physical van der Waals forces. So, we call it physisorption, physical adsorption. So, let us now try to understand the differences between physical adsorption and chemical adsorption. So, always keep in mind adsorption means some molecules are attracted and accumulated on a surface. The surface phenomenon is called adsorption. The one which provides the surface is called adsorbent. This is adsorbent. The one which comes and settles, the particles whose particles will settle on the surface are called adsorbate particles. So, based on the bonding between adsorbent and adsorbate, we have classified it into two varieties. If the attraction is van der Waals force, basic van der Waals force, we call it physical adsorption or physisorption or van der Waals adsorption. Had it been a chemical bond like this, it can be any type of chemical bond between adsorbate molecules and adsorbent, we call it chemisorption, chemical adsorption or activated adsorption. So, let us now go through the differences between these two varieties of adsorption and try to appreciate some interesting facts. See, they are coming. So, this is not adsorption because molecules are going into bulk. This is adsorption, just physical adsorption. See, molecules are just standing on the surface, they are not forming any bond with surface. See, just they are standing on the surface. See the chemical adsorption, they are forming a bond with it, they are forming a bond with the surface, that is chemisorption. So, in physical adsorption and chemical adsorption, that is the difference. In physical adsorption, the molecules have fallen on the surface, no bond. Here you see a bond, they are connected to the surface through a bond. So, what is this called? Chemisorption. So, anyhow, we will switch over. This is dissorption, escaping of particles. So, this is all the story. Now, let us switch over to concept of differences between physical adsorption and chemical adsorption. Physisorption and chemisorption, through van der Waals force adsorption, through chemical bonding adsorption. See, the physical adsorption is due to van der Waals forces. It is caused by chemical bond formation. Just now you have seen. Coming to the next point, it is not very specific in nature. What do you mean by that? It is not much specific. Means most of the adsorbates can just get physically adsorbed on any surface. Suppose there is some dust particles are in the room, they may settle on television screen, they may settle on some books. If you stand there, they may settle on your shirt, they may settle on your face as well as. So, there is no specificity for only this should get adsorbed on that kind of a thing. Why? Because it is van der Waals force of attraction. Van der Waals force of attraction is quite general. So, any particles can get attracted by any particles through van der Waals force. If you are there, they are brought together. So, the surface is receiving the particles through van der Waals forces. So, the particles can be anything, the surface can be anything. They will not put any conditions. The particle should be like this, they should have these features, or surface should be like this, surface should have these features, nothing like that. So, simply the physical adsorption can take place in any way it can happen. There is no unconditional, there is no condition. Unconditionally the particles of one substance can get settled on the surface. Coming to chemisorption, chemical adsorption is highly specific. Why? Because it is a chemical bond. So, suppose you just take an example, there is a surface, in this surface all particles are having lone pairs. On the surface the particles are having lone pairs. So, can ammonia like gas come and settle on this? No way, because ammonia also has lone pairs. So, who can come and settle on this? Somebody with vacant orbital, suppose there is some X with vacant orbital, it can come and settle. That is possible. Means what? It is highly specific. It will keep a condition. My particles are having lone pairs, so the adsorbate must have vacant orbital, or vice versa. Suppose the surface is having vacant orbitals, the particles are having vacant orbitals on the surface, whom will it attract? Whom will it attract? Now, will it attract any molecules with vacant orbitals? There is no chance. It will attract molecules with lone pairs. So, there can be a bond. So, for bonding to occur, it is conditional. All cannot bond with all. So, surface will have some features, and the adsorbate must have the counter feature such that there can be a bond taking place. So, the bonding to occur, there is a condition. It is not as general as in physical adsorption. It is not van der Waals force. So, for the bonding to take place, it is highly specific, highly specific. So, chemisorption is rare, highly specific. Physisorption is general, it can happen anywhere. Next point, reversible and irreversible. Who is reversible, who is irreversible? Physical adsorption is reversible, chemical adsorption is irreversible. What is the meaning of this? Suppose you keep the adsorbent, the adsorbate particles come and settle on this. At the same time, some particles will be escaping from it. So, it happens like this, and particles will be escaping also. So, there occurs an equilibrium between unadsorbed adsorbate and adsorbed adsorbate. Suppose if you expose some charcoal to some argon gas with some good pressure. So, the molecules enter the charcoal substance. At the same time, some of the adsorbed molecules will escape into the gaseous form. So, this to and fro phenomenon keeps taking place. This happens only in physical adsorption, and this is called reversible adsorption. There will always be an equilibrium between unadsorbed adsorbate and adsorbed adsorbate. Adsorbate means the molecules which settle down on the surface. So, adsorbed adsorbate and unadsorbed adsorbate exist in equilibrium. So, there will always be some equilibrium. So, that is called reversible adsorption. But here what happens, once an adsorbate comes and settles, it cannot be delinked unless otherwise you meddle with it. So, unadsorbed adsorbate may be there, but there can never be an equilibrium between them. So, that is why what we call it irreversible. Once a substance is chemically adsorbed, the adsorbed material will not exist in equilibrium with unadsorbed material, unadsorbed molecules in chemical adsorption. In physical adsorption, there will always be a to and fro phenomenon. Desorption and adsorption keep on taking place with equal rates at a saturated condition. Once the adsorption occurred around a surface, if you still keep some more adsorbate around, there will always be an equilibrium. So, this is how we work out the third difference. The fourth difference is it depends on the nature of gas, especially physical adsorption. The surface is innocent, it provides the surface, but whether the molecules to settle there or not, it all depends on the nature of those molecules, nature of that particular gas. All gases do not get adsorbed on a surface, common surface, with equal ease. You have got helium, neon, argon, krypton, xenon, helium to xenon, increase in molecular weight. Helium has got great escaping tendency. Xenon is being a big molecule cannot show that much escaping tendency. Diffusion of under a given set of temperature pressure conditions, helium has greater rate of diffusion than xenon, and that shows a tendency for them to be condensed. So, who will show a better condensing tendency? Xenon under a given set of conditions. One more thing you should remember, more easily liquefiable gases are more easily adsorbed. What do you mean by liquefaction of gas? You might have studied this in gaseous state. In gaseous state, in the critical phenomenon in Andrews diagram, you might have learnt this concept. Critical temperature is the temperature below which only a gas can be liquefied. Suppose I want to see oxygen in the liquid state, what to do? The first thing, do not compress. Really, what is the difference between gaseous state and liquid state? Gaseous state, the molecules are widespread, liquid state molecules are associated. So, what happens if you want to see a gas in liquid state, you should see that they are associated. So, that association to take place you have to compress, but the problem is before you compress you have to cool down the particular gas below its critical temperature, because above the critical temperature the gas can never be liquefied. The gas molecules will have sufficient thermal energy which will prevent them to overcome the intermolecular force of attraction, whatever high may be the pressure, whatever high may be the compressed extent. So, compression extent, whatever may be the extent, the thermal energy of the molecules above critical temperature will not let the molecules form a liquid. So, it is not possible to get a liquid, liquid form of a gas above the critical temperature. Therefore, the first condition, you must cool down the gas below the critical temperature before you start compression. Suppose you have got two gases A and B, you have got two gases A and B, its critical temperature is 80 degrees, its critical temperature is 40 degrees. What do you conclude? What is the first meaning of these two temperatures? A is such a gas which can be liquefied even above 80 degrees, and B is such a gas, A is such a gas which cannot be liquefied above 80 degrees, below 80 it can be liquefied. B is such a gas which cannot be liquefied above 40 degrees, it can be liquefied below 40. What do you understand? My first question is, can you liquefy B at 60 degrees? Can you liquefy B at 60 degrees? No way, because the critical temperature of B is 40. What is critical temperature? Above which a gas cannot be liquefied. Above 40 degrees B cannot be liquefied. Now I am asking you at 60 degrees. At 60 degrees B cannot be liquefied. What about A? A can be liquefied at 60 degrees because 60 degrees is below 80. What is 80? 80 is the maximum temperature where A can be liquefied by applying some pressure. At 60 degrees obviously you can liquefy because molecules have still less thermal energy at 60 degrees. At 60 degrees it is unable to get liquefied, at 60 degrees it is able to get liquefied because it has got higher critical temperature. So, greater the critical temperature means what? Even at a higher temperature you are able to liquefy that particular gas. That means the gas is showing a tendency to get condensed. Generally a gas which shows a tendency to get condensed means what? It has got ability to form van der Waals forces. So, once a gas can get condensed even at a higher temperature shows a tendency that the gas has got greater condensing tendency. So, it can get adsorbed on a given surface with greater ease. So, if you allow both A molecules and B molecules to settle on a particular surface, who has got a greater tendency to get settled? A has got a greater tendency to get settled because A's critical temperature is high. So, that adsorption, physical adsorption ability mostly depends on the gas which is getting adsorbed, not on the surface. So, it is the adsorbate that influences the extent of adsorption mostly in physical adsorption, because physical adsorption is basically dependent on the nature of the adsorbate, not on the adsorbent. It will not put any conditions. It is just van der Waals force. Whichever gas that is capable of forming good van der Waals forces can easily get adsorbed physically on the surface. Coming to chemisorption, it also depends on the nature of gas, but gases which can react with the adsorbent showed chemisorption. See, there should be a bond formed, even surface also should be capable of receiving the adsorbate molecules. It is conditional. So, surface must be ready to form a chemical bond with the adsorbent. So, it is not mere adsorbate that matters, it is adsorbent also is conditional in chemical adsorption. So, physical adsorption extent mostly depends on nature of adsorbate, chemical adsorption mostly depends on nature of both adsorbent and adsorbate. Coming to my next point, enthalpy of adsorption. In the beginning I told you adsorption phenomenon is a consequence of attraction between adsorbate molecules and adsorbent molecules. The attraction is more strong, more energy is lost. Attraction leads to loss of energy, stabilization of the system. So, if the adsorbate molecules are strongly attracted by the surface, what would happen? More energy is lost. If the adsorbate molecules are weakly attracted towards the surface, there is little loss in the energy. At constant pressure during a process, loss or gain of energy is called enthalpy change, delta H. So, delta H value low, 20 to 40 kilojoules of heat is lost during adsorption of molecules, gas molecules on a solid surface, because it is van der Waals force of attraction. Van der Waals force of attraction leads to loss of energy to a less extent. So, hardly if 1 mole of a gas is adsorbed, whatsoever may be the gas, the energy varies between 20 kilojoules to 40 kilojoules per mole. It shows that adsorption is very weak, van der Waals force is weak. Coming to chemisorption, you see the values 80 to 240 kilojoules, because it is a chemical bond. Because it is a chemical bond, the attraction is strong, more energy is lost. So, delta H is negative here also, but this is more negative, this is less negative, van der Waals force and a chemical bond. See, this is a very beautiful point. It is favored by low temperature, it is favored by high temperature. What do you mean by favorability? What do you mean by favoring? Delta G should be negative. If something to happen spontaneously, delta G must be negative. So, when can delta G be negative? Delta G is equal to delta H minus T delta S. Here also delta G is equal to delta H minus T delta S. And I told you pretty clearly in the beginning, delta S is negative for adsorption phenomenon. Why delta S is negative? The free molecules are settling on the surface. Free molecules are settling on the surface means what? They are losing their entropy. Once they are losing their entropy, delta S is negative. So, this value is negative. So, negative of negative, till here it is positive, and delta H is anyhow negative because it is attraction force. My simple question, is this negative more or less? In a physical adsorption, this negative value is a very less value, this is 20 to 40, this is a very small value. So, delta G is negative. For the process to take place, delta G must be negative, and delta S being negative, there is a minus sign before, altogether it will become positive. So, under what condition this will dominate this term? Settling of particles on the surface, settling of the particles on the surface, delta S wise both are almost same. So, who is the playing role? Who plays the role properly? See, here and here the difference is, here delta H is negative, here also delta H is negative, but here delta H is less negative, here the delta H is more negative. So, the scope of becoming delta G to be negative, only temperature should take the control. This negative value should dominate this positive value. When can this positive value be dominated by this negative value? When this is less. We can't have any control on delta S, you can have a control on temperature. So, better you keep low temperature. If you keep very low temperature only, this term will become less. If this term becomes less only, this will dominate this term and keep delta G negative. If delta G negative only, the process becomes spontaneous. Suppose you keep high temperature, what will happen? This term will become more positive and this will dominate this delta H negative value. So, quickly delta G becomes positive. So, if the temperature is high, this term will dominate this term and delta G becomes positive, and adsorption will not take place, instead desorption takes place, because in adsorption direction delta G positive means in the desorption direction delta G will be negative. So, particles will start escaping. A cold iron piece attracts dust, a red hot iron piece will not attract any dust. You have charcoal, red hot charcoal, that cannot attract helium, neon, argon, krypton, xenon like. whereas if it is a cold, very cold charcoal, it will catch up xenon, argon, krypton like substances, sulfur dioxide, methane, hydrogen like. So, you have to maintain a very low temperature in order to encourage physical adsorption. Van der Waals forces can occur only at low temperature. If you increase the temperature, Van der Waals forces will become weak and escape. But the effect of temperature on chemical adsorption is very peculiar effect. What is that effect? It is a chemical bond basically. Suppose you have the surface, the particle must form a bond. To form a bond, molecules must be activated, even surface must be activated, otherwise bond may not be formed. We have activation energy. Unless the molecules cross the threshold energy, you cannot have a reaction taking place. And basically this is what should I say, a reaction only, reaction kind only on the surface level of course. The difference between a normal reaction and this reaction is, in normal reaction the occurrence happens in the molecular level, but in this adsorption, chemisorption, the reaction will take place only on the surface, the bonds are formed only on surface. Even then, for the bonds to form, the molecules must be activated. In order to activate the molecules, one has to raise the temperature. In Arrhenius equation we have seen K is equal to A e power NaCa by RT. So, unless you raise the temperature, most of the molecules will not have activation energy. So, you have to raise the temperature very good, but there is a limit. If you raise the temperature too much, what will happen? You need high temperature to activate the molecules on the surface. Suppose the temperature is raised too much, again the same problem will come. Delta H minus T delta S is delta G. This is a high value, high negative value only, but if you raise the temperature too much, what will happen? This is anyhow negative, minus of minus plus. If you raise the temperature, this term plus term will dominate the minus term and delta G becomes positive. Delta G is positive means what? The process will not take place, again desorption takes place. How long can you increase the temperature such that the chemisorption takes place properly? As long as this T should not make this term dominating delta H. There should be delta G negative only. To that extent you can raise the temperature and see that adsorption take place easily. For chemical adsorption, temperature must be high to some extent, beyond that again desorption occurs. But physical adsorption, temperature must be low. No much activation energy is required. I just told you activation energy. The surface must be activated, the molecules must be activated for any bond to take place. But this is a weak bond, no much activation is required, just little activation also can make the molecule settle on the surface. But here high activation energy is sometimes needed, because we want a bond to form. There should be a bond taking place. So, the molecules must be activated. So, energy of activation is high. So, for this energy of activation is high, for this energy of activation is low, for this delta H is negative, for this also delta H negative, but it is less negative, that is more negative. See, there is one more beautiful difference between physical adsorption and chemical adsorption. You have already seen in the visuals that in chemical adsorption layer over layer are formed. In physical adsorption only one layer is formed. How that has happened? See, once you have a layer, once a layer of molecules are on the surface, after all the attraction is van der Waals force. So, there can be one more layer settling on this. That is also van der Waals force. For van der Waals force there is no specificity. Any molecule can be attracted to other molecule through van der Waals force. You painted the wall for first layer, second layer can be painted on the first layer of the paint. They are held together by van der Waals forces. But here what is happening? You have got some, suppose you have got some vacant orbitals on the surface. So, adsorbent must have a lone pair, it forms a bond. Like that. But now can one more layer of X will settle on this X? No chance. Why? Those X atoms will bring lone pairs, but these X atoms do not have vacant orbitals. So, once a layer of particles are settling on the surface with bonds, they may not be able to form a bond with the next layer. So, in chemisorption it takes place only unilayer. In physisorption it is multi-layered. You have seen in a visual one layer, next layer, that is physical adsorption. In chemical adsorption there is only one layer formed. See, depends mostly on the adsorbate. Here depends on adsorbent and adsorbate, both actually depends on both in this case. That is what we have already discussed. Suppose I have got coconut charcoal, that charcoal is a very good adsorbent. In that adsorbent I want to, I will expose it to sulfur dioxide, methane, hydrogen like gases. Will all of them be settled with the same ease? There is no chance, because it depends on their ability to condense. SO2 has greater ability to condense than helium, because helium has a greater escaping tendency, SO2 has greater condensing tendency. So, mostly adsorbate matters in the adsorption phenomenon, physical adsorption phenomenon, whereas in chemical adsorption phenomenon it depends on both adsorbent and adsorbate. Many times I told you, because both must have countervalencies, one has a lone pair, the other one has a vacant orbital and vice versa. If one has a unpaired electron, the other fellow also must have unpaired electron, then only a chemical bond can form. But here bond cannot be formed, there is a layer of particles, it is only the condensing ability of the adsorbate. So, just you can now after seeing the differences between them, you can again visualize the phenomenon. You see this, that the loveliest aspect of chemical adsorption, chemisorption. See, this is a bond, this is adsorbate, this is adsorbent, this is adsorbent and this is adsorbate. On the surface there is a single layer. See, there is a dip kind of a thing here. In that dip the molecule is settling. Now, how can the other molecule be attracted to this in that phenomenon? There is no scope. So, chemisorption is a single layer adsorption. It is a single layer adsorption. By seeing this you can decide it is chemisorption. See this now. Before the name comes you can tell this is physical adsorption. Why? Because there is only van der Waals force. Try to understand, it is not penetrating, the molecule is not penetrating into the surface. There is no bond, just van der Waals force of attraction. In the previous case, see there is a bond. See, everywhere you can see a bond. The molecule has formed a bond with the surface molecules in chemisorption, that is why it is single layered. Here there is no bond, just van der Waals attraction. So, once a layer forms van der Waals attraction, second layer can form van der Waals attraction with first layer, third layer can form van der Waals attraction with second layer. So, it is multi-layered adsorption, physical adsorption, there is no bond, that is why just 20 kilojoules. In the previous case it is about 80 to 240 kilojoules per mole. That adsorption is very strong, chemisorption is very strong, physisorption is very weak. This is reversible as well, they can also escape. So, what I would like to tell now, we have first understood some beautiful words: absorption, sorption, desorption, adsorption. So, we have focused only on the phenomenon called adsorption because it is a surface phenomenon. In that adsorption, we have seen two varieties of cases. One is physical adsorption, the other one is chemical adsorption. In the physical adsorption, the adsorbent and adsorbate are attracted by mere van der Waals forces. In chemical adsorption, the adsorbent and adsorbate are attracted by a chemical bond. In physical adsorption, it all depends on the nature of adsorbate mostly. In chemical adsorption, it depends on both adsorbent nature and adsorbate nature. And in physical adsorption, delta H negative value is very less, 20. Chemisorption it is about 80, 240 also it will be there. Delta S is negative in both cases almost to the same extent. Maybe because it is multi-layered, in physical adsorption delta S may be a little more. Whatever may be the case, in order to keep delta G adsorption to be more negative, the temperature must be kept low in case of physical adsorption. Physical adsorption is mostly favored by very low temperature, whereas chemical adsorption has a control. You have to increase the temperature to an optimum extent in order to activate the molecules and the surface. Once molecules and surface are activated, you can go for chemisorption, and if you go beyond certain temperature, what will happen? Delta G becomes more positive. Once delta G becomes positive, desorption starts taking place. So, in chemisorption there is an optimum temperature you have to maintain. And the most beautiful aspect is in physical adsorption, the gases with more critical temperature can get adsorbed more. Suppose you have SO2, methane and hydrogen. The critical temperatures are in this order only. Tc stands for critical temperature. Greater the critical temperature, greater the tendency of the gas to get adsorbed. So, SO2 can adsorb more extents on the same surface. Suppose you have charcoal, on this charcoal more SO2 will come, less CO2 will come, less H2 will come. Extent of adsorption of SO2 will be more, because SO2 has got greater tendency to get adsorbed, because it has got greater critical temperature. Do not get confused between critical temperature and temperature of adsorption. Adsorption temperature should always be low, whatever may be the gas coming, in order to keep the van der Waals forces safe. Van der Waals forces cannot exist at high temperature. So, you should maintain low temperature in order to maintain van der Waals attraction. Van der Waals adsorption, physical adsorption. So, physical adsorption is mainly favored by low temperature. This is critical temperature. High critical temperature is favorable. High critical temperature. Critical temperature is a characteristic value for a given adsorbate, for a given gas. A gas with high critical temperature will have greater tendency to get condensed. So, such gases are more easily liquefiable, and such gases will show greater tendency to get adsorbed on a surface. In these three, if you observe, or you take helium, neon to xenon, as you move like this, critical temperature increases. So, will helium get easily adsorbed or xenon get easily adsorbed? So, xenon can be easily adsorbed. So, this is how mostly adsorption extent depends on, physical adsorption extent depends on mostly adsorbate. Low temperature is favorable, multi-layer adsorption, physical adsorption, chemisorption is single layered adsorption. So, where we observe these adsorptions and all, what are the applications? Why should we bother so much about the phenomenon of adsorption and physical adsorption and chemical adsorption? Before going into those details, first let us first understand what are good factors, what are the factors that favor or unfavor the adsorption phenomenon, and we will take up only mostly gases on solids. You take a solid substance, how good a gas can adsorb on the solid substance we will see now. Factors affecting adsorption means first of all nature of adsorbent. Nature of adsorbent will decide how good adsorption takes place. What do you mean by this nature or state of adsorbent? What is the very good condition of an adsorbent? It should provide its surface. What do you expect from an adsorbent? You expect an adsorbent to attract molecules of the other substance. So, adsorbent should be a good surface provider, should provide the surface. I will show you a small beautiful example. You see, suppose this is an iron piece or a wooden block, I can say wooden cube. You got a wooden cube. I want to paint this wooden cube. It requires some paint. I will cut this wooden cube into two pieces. What will happen? I will have two pieces like this. It is already painted. One more piece. This is also painted already. You see this? I have broken this wooden piece. The wooden piece is completely painted outside. If I break it into two pieces, what did you observe? Even back side also it is painted. It's painted all sides. Everywhere it is painted. But after breaking into two pieces, what happened? There are two surfaces developed, unpainted surfaces. See, these two surfaces are not painted. So, they are still available for what? Getting painted. So, means what? You require extra paint to paint it. Suppose I break it into further like this. Again two more pieces will come and there will be some unpainted surfaces developed. If I again vertically break it, some more surfaces will come. So, if I keep on dividing a wooden piece into parts, some more extra surfaces will develop. So, what do you understand? If you have a big block, if you keep on breaking it into pieces, its surface area will keep on increasing. As the surface area keeps on increasing, that material will be able to absorb more particles of the adsorbate. So, what do you conclude? A substance which is in more divided form is capable of adsorbing more substance, more adsorbate. So, the adsorbent must be mostly in what form? It should be in most divided form. Instead of being in a combined form, it should be in a divided form. So, if you have a nickel piece, that is not a good adsorbent. If you have nickel powder, this is a good adsorbent because this has got lot of surface compared to this. When you are breaking it into pieces, the surface is being divided into much more extent. So, this powder will be able to catch up more molecules onto its surface. So, the number of molecules that can be adsorbed on this will be less number of molecules that can be adsorbed on this divided form will be more. And some substances by nature will be very porous. What do you mean by porous? Porous means what? There will be holes in it. Holes like suppose sponge. If you can see into the sponge, there will be so many cavities. Bulk cavities will be there. Within the bulk you will find some cavities. Each cavity has a wall and each wall provides its surface. Suppose you have got a porous substance, it will be like this. Everywhere you will have pores. These are all pores. For the pores there is a surface. The surface can take up molecules. See, the surface can take up some molecules. Porous materials are better, more capable of taking the adsorbate more. Porous materials like we have got silica gel, we have got activated charcoal. I will tell you what do you mean by activation. Activated charcoal, silica gel, and you have got alumina gel we have got. These are all good porous materials. They can provide more surface area. So, they are very good adsorbates, the adsorbents. That is the reason while separating the inert gas mixture, in the air you will have inert gases somewhere around 1% or something like it. So, if you collect that mixture of inert gases, the individual inert gases can be separated by Waals method. In Waals method he used only coconut charcoal, activated coconut charcoal, on which the inert gases can be differentiated, adsorbed at different temperatures, preferentially adsorbed basing on their critical temperatures. And of course, the selected adsorbent is porous, very porous and activated. What do you mean by activated substance? The surface that has no adsorbed material is called activated surface. Suppose you have charcoal, you heat it with superheated steam, 1000 degrees steam, you just pass over surface, all the pre-adsorbed material will escape. Suppose you have got a charcoal piece, this is a charcoal with some pre-adsorbed material, this is all. If you pass steam over it, this is steam, 1000 degrees steam. What will the steam do? That will have lot of kinetic energy. It will take away the pre-absorbed material. Now what is this? Activated. So removing of pre-adsorbed material is called activated surface. So the adsorbent must be well divided so that it can provide more surface. The adsorbent must be porous in nature and the adsorbent must be activated. So it mostly depends on the nature of adsorbent. Adsorbent must be divided into granules, the adsorbent must be free from pre-adsorbed material, the adsorbent must be having pores, then only adsorption will take place in a better way. We will continue. Have a good day. We will meet in our next session. Thank you.